Okay, so welcome to the video. In this video, we're going to be talking about the Bramble-Hilbert Lemma. Um, and specifically, we're just going to discuss it and go over some examples to show you how to use it. We will not prove the lemma here, um, but I will give you, if you want to see the proof, it is in a book that I'm going to be referencing. And in order to understand this video, you will probably need to know a little bit of functional analysis, like Sobolev spaces, and just some general advanced math knowledge. Okay. Um, the reference that I'm specifically going to be using is this book here, Numerical Treatment of Partial Differential Equations. That's by these three authors, and the date is I think 2007. Um, And the reason being, well, if you look at, say, the Wikipedia article for the Bramble-Hilbert lemma, you'll see all different variations of this lemma. There's all just different versions. So I just like the way this book um, does the lemma, and so I just want to present specifically this version, and it's kind of a more general version of the lemma, which I find to be more useful. Um, and I just personally like the one that's outlined in this book. Um, so yeah, we can go ahead and jump into it. So let's look at what the lemma is. Okay, so I'm just going to shorthand notation it, the Bh lemma. Okay, so what is this lemma? Let D, let me write that a little bit better. So let D, a subset of RD, okay, be a bounded domain with Lipschitz boundary. Okay, I'm going to shorthand the notation sometimes. So Lipschitz boundary. So D is the spatial dimension. So capital D is our domain. Okay, it's going to have Lipschitz boundary, so we're not going to have any kind of funky objects. We're going to let Q. So Q is going to map HK plus 1. So this is the Sobolev space to R. Okay, so it's a Sobolev space where k plus 1 derivatives are L2 integrable. The order k plus 1 up to the order k plus 1 derivatives are L2 integrable. Um, yes, that's the space. And they're going to map to R. And specifically, we'll let k, so k can be any number between 0, so any integer, really, okay, including 0. And it's going to be such that it's going to be a bounded sublinear functional. Okay. Um, if, and I'll talk about some of this stuff in a moment. So if Q of P is equal to 0 for all P in PK, then we have this result here. We have that absolute value of Q of, say, V is bounded by a constant V, and I'll say what this is in just a moment. So it's bounded by V in the HK plus 1 semi-norm. Okay, not the full norm, but the semi-norm. Okay, so this is the lemma. And this lemma, it's a tool that's used in finite element analysis. Okay, I won't go into all the details about, specific. It's mainly used in error analysis, um, and we're not gonna go into all the error analysis business. We're gonna look at just some small parts of what happens, so you can get an idea for how this lemma is applied. Um, and so again, Q, it needs to be a bounded functional and sublinear. Okay, and if you're thinking, okay, well, what's a sublinear functional? Typically, you think of a norm as being a sublinear functional. You know, that's an example of one. So we'll see some examples that kind of shine a light on what's going on here. Okay, and it's also important to notice that, let me change the color. Okay, so that did not change the color. So this K is one less than the Sobolev space that you're in. Okay, so we're in HK plus 1, but we're 0 on polynomials of degree K. Okay, and there is no, you can be, it doesn't have to be 1D, it can be a multi-dimensional polynomial. Okay, a polynomial with, uh, yes, in multi-dimensions. Okay, so there's a few things to note if you're not already familiar. So that is, well, what is bounded? Okay, you probably already know this, but just in case. If your functional is bounded, then absolute value Q of V is bounded by a constant times the full norm. Okay, the full norm. So what the lemma gets you is that you don't get the full norm, you get just the semi-norm. Okay, and the other part is, well, what does sublinear mean specifically? So sublinear. Okay, that means Q of V plus W is bounded by Q of V plus Q of W. Okay, so it's like triangle inequality. And also, if you have Q of a constant, say alpha times V, this is equal to alpha Q of V, and this is for positive alphas. Okay, so if alpha is a positive constant, you can pull it out of your sublinear functional. Okay, and what else is there to notice? Okay, anything else worth mentioning? Oh, right. The other important thing to mention is, well, this constant C is dependent on your domain. Okay, it's dependent on, several other things, but in particular, it's dependent on your domain. Okay, so that's an important thing you need to consider when you're applying this lemma. Okay, and because it's dependent on your domain, that's how it is used in the finite element error analysis. Because you look at the element sizes and you can pull out orders of H. Again, I don't want to go into all of this. We're just going to look at how to use this lemma. Okay. So let's continue. Let's go ahead and just jump into an example. Okay, so example 1. Okay, so let capital pi is going to map hk plus 1 d to pk. Okay, and we're going to let it be a projection. Okay, we're just going to keep it general for now. So that is that pi of p equals to p for all p in pk. That's the important feature. Really, if you apply the projection to itself, you get the projection again. Okay, so projecting a polynomial just gives you the same polynomial. Okay, and the idea of projection shows up again a lot in the finite element analysis. And so what you tend to look at is you look at the error between a function and its projection. And we'll say in the L2 norm, we're going to measure the error here. So for v in h, k plus 1 d. Okay. So what we can do is, well, call q. So say q, we're going to define it as this mapping here. Okay. You plug in q and you get this number, whatever it happens to be. In particular, we can write this as, now the trick here is to write this as the identity map. Okay, the identity minus the projection of v. Okay. So this is our map, and well, let's see, is it bounded? We want to ask ourselves, is this a bounded map? Okay. So we take q of v. Well, this is an operator applied to some function v. So this is just the norm of that operator times v in the L2 norm. And this L2 norm is bounded by, again, I'm just writing it again. It's certainly bounded by the hk plus 1 norm. Okay, and again, I'm assuming that you do know some functional analysis, so you know why this is the case. And really, it's just that you have extra terms in this norm. Okay. So this norm of the identity minus the projection is just a constant. So you have a constant times the norm of v. So q is bounded. Okay, so q is a bounded functional. Is it sublinear? Well, if you take q of v plus w, this is what you expect. This is v plus w. And I'll just go ahead and spoil the details. Well, you can break it apart and apply triangle inequality. And yes, you will get q of v plus q of w. And again, same with a constant. If we plug in a constant here, we will also get out alpha q of v, and this is for alpha greater than or equal to 0. Okay? So yes, we have that q is a sublinear bounded functional. Okay, well, the last thing to check is q of p. And here we're assuming p is a polynomial of degree k. So this is the identity minus pi of p. Okay, but remember, the projection of a polynomial is just a polynomial itself. So in this case, this is just identically 0. Okay, so by the Bramble-Hilbert lemma, what do we get? We get that q of v is bounded by some constant times the seminorm of v. Okay, and it's kind of, again, we didn't specify the space d, we didn't pick a k, but really the important part is that we are using this for measuring the error of a function minus its projection. Okay, the difference between the projection and the function itself. Okay, and again, the constant is dependent upon the domain D. Okay, so that's example 1, and this is a very important one as well. So next up, we have example 2. Okay, I'm just going to pull it out. Right. So this one's a little bit more concrete. We're going to let D So one moment. So D is going to be the interval minus 1 to 1. We're going to let K be 1. And we're going to define our functional. So Q of V is going to be the absolute value of the integral from minus 1 to 1 of V minus 1 half V of 1 plus V of minus 1. Okay. So if you're not really, this might look kind of strange if you're not familiar with the subject, but what this functional represents is here we're measuring the error between an exact integral and a quadrature rule. Okay, so we have the exact integral minus the quadrature rule, and we want to see how close this quadrature rule approximates the integral. Okay, um, and let me, oh right, and so again, this is for V in H2. I'm going to write minus 1 to 1 like that. Okay. Technically, I should put another parentheses, but it gets clunky. All right, so we have this functional, and we're going to check the different bits of information. So let's see if it's bounded, if it's sublinear, and if it's 0 for polynomials. Okay, so maybe the trickiest one is actually to show that it's bounded. So let's go ahead and look at that. So if we take the absolute value, and we can do triangle inequality here. So we're going to do several different inequalities. Again, I'm assuming you have some, advanced mathematical knowledge that you understand what I'm doing at this step. Okay, and if you're not sure, you can always ask in the comments. Okay, so I just did triangle inequality and moving the absolute values inside. Okay, so we have this here. Keep in mind where we're trying to go. We want to get to the hk plus 1 full norm. Okay. So in this Sobolev space, our functions are square integrable. So right now we have the integral of just v, but we want it to be v squared. Okay. And the way that you can do that is to apply Cauchy-Schwarz. Okay, I'm not going to talk about that. I'll assume that you know how to get that. And what that does is it gets us the L2 norm of v. Okay, so if you apply Cauchy-Schwarz to this integral, you should arrive here. And I wrote d, let's write minus 1, 1. Okay. Here, we can take the max, and functions that are in H2 minus 1 to 1. So functions in H2 in one dimension, they are actually they are continuous functions. So yes, right. We can just, yeah, okay. They are just continuous functions, so we can take the max. Okay, so really we're going to write here as v in the, should I write this C norm? C 0 minus 1 to 1. Okay, so this is the max norm. Okay, I'll just write it here, the max norm. Okay, and again, we're going to use one other trick here. Here, this is bounded by the H2 norm. And there is a result in functional analysis. Because we're in 1D, this max norm is actually bounded by a constant. I'm going to write, let's say beta. Okay, I don't know what constant, let's call it beta, times V in the H1 full norm. Okay. And so to conclude, we can take the max of square root 2 and beta, and then we'll get this norm here. Okay, so we just bump this norm up to the H2 norm because it includes more terms, and we take the max of square root 2 and beta, and we get this. Okay, so this functional is a bounded functional. Okay, I'm going to leave, you can check the sublinearity. I'm not going to do that here, but it's not that hard. You can check it yourself. And the other thing is to check that we want to say that Q of P is equal to 0 for all P in P1. Okay. So how can we do this? Well, let's just write P as AX plus B. Okay, some arbitrary function. Then Q of P is equal to the integral, maybe write that, from -1 to 1 of AX plus B dx minus 1/2, and remember the quadrature rule we're using, so we are plugging in 1 and -1. Okay, so this is A plus B plus negative A plus B. Okay. I'll mention here AX, let's highlight it. So AX is an odd function on a symmetric interval about -1 to 1. So its integral is going to be 0. Okay. And so what that means is that this integral is just going to be 2b. Why is that not right? Yes, so I did make a mistake. Let me correct this. We do not have this 1/2 here. Okay, so there's no half. Yeah, this is kind of a hassle, but we'll go with it. I'm not going to redo it. Yes, I wrote the quadrature wrong. Okay, so maybe you noticed that at the beginning, but I messed it up. So there should be a 2, and a 2 there. And that means we get rid of this 1/2 here. Okay, so I'm just modifying the problem as I go. Okay. Now we should see that this does work out as I had originally intended it to. But this will be 2b. And here the a's cancel, and we get also -2b. Okay, so it's 0. Good. So assuming sublinearity holds, we have Q is a bounded functional, and it's 0 for first degree polynomials. So what does that mean? So by the Bramble-Hilbert lemma, we have that the error in the quadrature is bounded by a constant times V in the H2 norm. Okay. And that concludes the video. Just some last remarks. When you apply the Bramble-Hilbert lemma, you really uh, are not going to know what that constant is going to be. So you just throw in that constant, and it's dependent on your domain and the order of the Sobolev space and all those kind of things. So you're not going to have any knowledge about that. Okay. Um, but other than that, I think that's about it. And again, I didn't copy the book exactly. Um, I modified it a little bit just for my own personal uh, perspective. So that'll do it for this video. Let me know if you have any questions.